In the previous video, we talked about basic elements of multivariable calculus, such as vectors, curves, surfaces, etc. We also talked about unit vectors and introduced addition of vectors and multiplication of vectors with scalars. Now, we will continue and talk about how we can multiply vectors with each other. What is important to remember about math is that we can choose which operations we define for vectors. So the question we should ask is, which types of multiplication operations on vectors would make sense for practical applications? Let us start by creating unit vectors x hat and y hat and add two vectors a and b. Call the angle between them theta. I will now introduce the unit vector a hat, where the vector a can be written as its length multiplied by a hat. I will also introduce the unit vector a n hat, which is perpendicular to a hat. The next step is to divide b into one component that is parallel to a and one component that is perpendicular. This will be achieved by writing b using the unit vectors a hat and a n hat. We find that the parallel part is given by the length of b multiplied by cosinus theta. And the perpendicular part is the length of b multiplied by sinus theta. Hence, we write b as b parallel a hat plus b perpendicular a n hat. Now we can introduce the first way of multiplying vectors. The dot product has the length of a multiplied by the parallel part of b. The symbol for the dot product is the dot between the vectors a and b. We can insert expression for b parallel, which is b cosinus theta. This expression is symmetric, which means that if we would have started with the vector b and taken the part of a that is parallel to b instead, we would get the same value. The other operation is to multiply with the perpendicular component, which we will call the cross product. The cross product will be a vector, which I will talk more about in the next video. Here, we use that the length of the cross product is a times the perpendicular part of b. If we insert expression for the perpendicular part of b, we get that the length of the cross product is ab times sinus theta. Assuming that we're using Cartesian coordinates, it can be useful to write these operations in terms of the coordinates instead. To do this, start by introducing the angle phi between a and the x-axis. If we use the expression for rotation of the coordinate system we derived in the previous video, we get that b parallel is bx cosine phi plus by sinus phi, and b perpendicular is by cosinus phi minus bx sinus phi. From trigonometry, we can also see that cosine phi is ax over a, and sinus phi is ay over a. Now, let us find a new expression for the dot product. Start by replacing b parallel with its expression in terms of the angle phi. Then replace cosine phi and sinus phi with our expressions in terms of a. A will cancel. And we get that the expression for the dot product is ax times bx plus ay times by. Let's do the same for the cross product. Insert expression for b perpendicular. Insert expression for cosinus phi and sinus phi. A will cancel. And the final expression for the length of the cross product becomes ax times by minus ay times bx. Since we commonly represent our vectors by the x and y coordinates, these expressions are usually easier to work with than using the angle theta between them. As this video will focus on the dot product, we will leave the cross product to the next video. The dot product is what we call a scalar product, as it gives a scalar value. Scalar products are actually a very important concept in math, and if you take more advanced math courses, you will likely see more of them. I will start by giving you the motivation why multiplication with the parallel part of two vectors is important in physics. The first example is mechanical work, which represents the energy that is added or removed from a system. Start by assuming that we have one object, here represented by the green circle. Then add a force to the right. Now assume that the particle travels on a straight line with length s to the right. The force will cause the particle to accelerate and adds kinetic energy. The energy added is work, and in our first mechanics class we probably learned that work is force times distance. Assuming that we started from rest, the work should now be the kinetic energy of the object mv squared over 2. In the general case, we say that the work is the change in energy. Let's show another case with the force to the right. This time the object will move down. This would cause the object to move in a circle, just like the moon orbits the Earth. Here, we are no longer changing the kinetic energy of the object, we are only causing it to turn. Hence, we got that in the first case, when the force was parallel to the motion, we added energy. But in the case when the force is perpendicular, the kinetic energy stayed the same. Hence, we get that it's only the part of the force that is parallel to the motion that will add energy. We can therefore change f in the expression for work to f parallel. We can also note that the curve s that we're moving along has a direction, and hence add the vector notation to it. Multiplication by the parallel part of a vector is the dot product. If you want to be strict from a mechanics point of view, the force could change value during the motion. Hence, the actual expression for work is to take the integral of the expression along the curve s. More on this topic in the integrals video later in the series. One other example from physics that we'll encounter a lot in fluid mechanics is flow through a cross-section. Assume that you have a pipe with a flow velocity v. Now, define a cross-section which mathematically is a surface that covers the entire pipe. Call its area A and add a normal vector n hat. If you want to know the flow through this cross-section, it will simply be the velocity times the area. However, if we rotate the cross-sectional area, we realize that the flow through it will decrease. And when it's parallel to the flow, no flow particles will pass through the cross-section. Let's rotate the cross-section back a bit and define the angle theta. From trigonometry, we can now find that the flow is VA times cosinus theta. As theta is the angle between the normal vector and the velocity, we find that the flow is the dot product between the velocity and the normal vector, multiplied by the area of the surface. I hope these two examples show that multiplication with a parallel part of vectors is commonly occurring in physics. Let us continue and talk about some properties of the dot product. If we take the dot product of a vector with itself, the angle theta will of course be 0, as the vector is parallel to itself, and the result will be the length of the vector squared. We can therefore express the length of any vector as the square root of the dot product of the vector to itself. The dot product for vectors is commutative, which means that the value is the same even if you change the order of A and B. Our next question is, what is the dot product of A with k1b plus k2c? To investigate, let's bring back our vector A and the unit vectors a hat and a n hat. The vector A will simply be its length A times a hat. Let's bring back vector B expressed in the unit vectors a hat and a n hat. And finally, add the vector C also expressed in a hat and a n hat. The dot product is the length of A multiplied by the parallel parts of B and C. As this is a traditional scalar expression, we can distribute A. AB parallel is the dot product between A and B, and AC parallel is the dot product between A and C. Hence, we have the bilinear property that we can simply place the dot product inside the parentheses. The dot product is not associative, as A dot B is a scalar and the dot product requires two vectors to work. Hence, A dot B dot C is not defined. If we use one dot product and one scalar vector multiplication instead, A multiplied by B dot C would not be the same as A dot B multiplied by C. A simple way of seeing this is to consider that A multiplied by B dot C is A multiplied by a scalar, and hence in the direction of A. A dot B multiplied by C is a scalar multiplied by C, and hence in the direction of C, which is different direction than A. Finally, if A dot B equals A dot C, what would we know about B and C? As the dot product is multiplication with the parallel part, we know that B parallel is equal to C parallel. The perpendicular parts can still be different though, as we see in the example. The next topic is projection. Assume that we know A and B and want to calculate the value of B parallel. This would be the scalar projection of the vector B on the vector A. We can relatively easily get an expression for B parallel from the dot product. Simply divide by its length A. We know from the definition of unit vectors that the vector A divided by its length is the unit vector A hat. Next, assume that we want to create the vector corresponding to B parallel. As the vector is in the A hat direction, the vector will be B parallel A hat. We can obtain an expression for this vector by inserting our scalar projection for B parallel. This is what we call the vector projection, which is the part of vector B that is pointing in the direction of A. If we want to express it in terms of our vector A instead of the unit vector, use that A hat is the vector A over its length. The next question is, how can we calculate the perpendicular vector of B? If we know the a n hat vector, we can simply use the same equation for projection, but with a n hat instead. Moving on, the next topic is orthogonal vectors, which means that the angle between the vectors is 90 degrees. If two vectors, here C and D, are orthogonal, the dot product will be 0, as they do not have any parallel components. Another example of orthogonal vectors is the perpendicular projection of B, which is orthogonal to A. X hat and Y hat are also orthogonal to each other. A closely related topic is orthonormal vectors. Here we will require that the vectors are orthogonal and both vectors have the length 1. If the length is 1, we can write them as unit vectors. Examples are x hat and y hat, which are orthonormal to each other. A hat and a n hat are also orthonormal. In general, we want our basis vectors to be orthonormal, as that will make our calculations much easier. As we made C and D orthonormal, we can use them as basis vectors to describe vector B. Vector B can therefore be written as BC C hat plus BD D hat. However, BC can be written using the projection of the vector B on the C vector. And BD can be written as the projection of B on the D vector. The vector B is therefore given by B dot C hat in the C hat direction and B dot D hat in the D hat direction. This is a very useful expression, as we simply can rewrite the vector B in any orthonormal basis by simply using the dot product. To illustrate once more, let us use the expression to write the vector A in terms of C hat and D hat. We first get the AC component. And then the AD component. Finally, let us move to 3D. The expression for the dot product will simply add AZ times BZ, similar to the other terms. To illustrate projection, we first need the third unit vector E hat, which is orthonormal to both C hat and D hat. In an orthonormal basis, all unit vectors should be orthonormal to all other unit vectors. To describe B, add the E hat direction, which also can be obtained by projection. Now we have the BC component. We have the BD component. And the BE component. Note that when we use an orthonormal basis, we can calculate the coefficients in any direction independent on the other directions. To illustrate how useful an orthonormal basis is, I will show what happens if you try to use a basis vectors that are not orthogonal. Assume that we want to describe the vector B in terms of vectors C and D. We write B equals BC C plus BD D. If we try to calculate projections on the C vector and then the projection on the D vector, then, when we add them together, we will no longer obtain the vector B. Note what happens when we change the direction of D. It is only when the two vectors are orthogonal that we can obtain the coefficients by simple projections. And as long as they are orthogonal, any rotation of C and D will reproduce the vector B by projections. The next question is, how would we calculate the coefficients when vectors no longer are orthogonal? Start by rewriting the vector B in terms of x hat and y hat. Do the same for C. And same for D. Now, collect all coefficients belonging to x hat, which will have to be equal. And collect all y hat coefficients. We now have a system of linear equations, which we can write on matrix form if we prefer that notation. Hence, we see that we have to solve a system of equations to calculate the coefficients in the non-orthogonal case. This will be more complicated than simple projections, especially when we increase the number of dimensions. Let us illustrate this solution in the figure as well. Watch how both coefficients change value when we change the direction of only the D vector. This is different from the orthogonal vectors when the coefficients are independent on each other. If we use non-orthogonal vectors, should also be careful what happens when the vectors are close to parallel. This works, but we describe B with two very long vectors, which, if we ever work with approximations, tends to give large errors. In the limit case, where the two vectors are parallel, this will no longer work. One way of testing it if it works or not is to calculate the determinant of the linear matrix to solve, which should be non-zero. Here I will assume that you have taken a linear algebra course and heard about determinants before. But I will do a quick repetition what it is, as it will appear several times more in this course. For a 2 by 2 matrix, you calculate the determinant by taking the diagonal terms minus the anti-diagonal terms. But the question is, what does this value represent? Let us look at the vectors C and D. Assume that these two vectors create an area A. The 2D determinant will then be this area. The largest area we can create is when the vectors are orthogonal. While this area goes to 0 when the vectors are parallel. Let us do the same illustration in 3D. We'll first add the vector E, as we need 3 vectors to describe B in 3D. The system equations will now become a 3 by 3 system. One way of calculating the determinant is to start with Cx and then take the 2 by 2 determinant in the y and z directions of D and E. Continue with the same for dx and the 2 by 2 determinant for E and C. And the same for Ex, multiplied by the 2 by 2 determinant. To illustrate it graphically, let us add the 3 vectors. The determinant will now be the volume that these 3 vectors will create. As soon as all 3 vectors are in the same plane, the volume will be 0, which we will see when we rotate the volume. With this, I will end this video, and in the next one, we will focus on the cross product instead. Thank you.